Okay, thanks YouTube. Where is the slide? Where was I? Okay, so I've been talking for 6 minutes and YouTube was being stupid, and I tried this before when I was doing this workshop, and between the workshop and this stream they appear to have added a button that you need to click to go live instead of just clicking your button in my streaming program. So hi, this is Hacking in C, and this is the first lecture, so let's get started. I'm going to talk today about first the introduction, more or less, who and what, and then I'm going to talk about some other things. So let's get started. I will try to keep an eye on chat, but it's also slightly hard, so and if you chat in there too much, then it's a bit hard for me to follow what is a question and what is off topic. So if you would like to keep the memes in a lecture chat and the questions in the YouTube chat, that would be great. If you can't hear something or something like that, then the chat would obviously also be a good place to go to. Yeah, so let's get started. So personnel first. I'm Tom. You can reach me on this email address. I am a PhD candidate. That's the third thing. So I am not a regular lecturer. I'm taking over for Peter Schwabe this year. I'm a PhD student of his, and I do research into post-quantum crypto. And what that is cryptography that should be resistant against the quantum computer. And if I were to summarize my research in a sentence, then it would be saying, I'm making the internet post-quantum. So I'm doing research into post-quantum TLS at the moment, and also looking into some other things down the line. So yeah, my supervisor is Peter Schwabe. Peter Schwabe is the original lecturer for this course. I'm taking over for him this year, and that is because he is on sabbatical. Sabbatical is a sort of vacation where you save up your holiday hours for a few years. And then if you do it for research purposes, then the university gives you extra holiday hours, and then you can go elsewhere for a few months and work on some new research topic or learn something you didn't know before or something like that. Of course, so Peter went to Portugal, then this happened, so I think his sabbatical is looking a bit like this now. But yeah, he's still working on formally verified implementation of cryptography, I think. Other people involved. Quite a few of you already figured out that Eric Pol is the course coordinator. That is a thing on paper. I am not official faculty. As a PhD candidate, I'm temporary staff or junior or whatever, and I'm not allowed to give grades in theory. I can give grades, but I cannot be responsible for them. So Eric Pol is our paperwork guy, although in practice, you should contact me. Unless you have a problem with me, then go to Eric Pol, or to any other person at the university, but I hope I should usually be contacted in the first place. And then we have Denisa. She's in charge of tutorials. She's a fellow PhD candidate. And then we have a bunch of student assistants whom you have probably already met on the Discord, and they are these people. Okay, so course layout. That is the what section of this introduction. So we have this syllabus on the website. It lists a bunch of things, such as that I had a typo in the time of the first lecture at the start, so I fixed that today. Some practical stuff, links to Discord, Brightspace, Osiris, and a preliminary schedule is here. So you can see here that we're going to be talking about some, so this introduction, C programming language, types, pointers, and some things about the course website, information about the lectures. So, for example, that they will be live streamed on YouTube. You can chat, and recordings will be made available. And some things about how the homework will work, so that you have to hand in stuff, and that's some preliminary information on the exam. So I don't know what's going to happen with the exam yet. We're probably going to be doing assignments and a report, because it's quite probable that there will not be any written exams at the university at the end of this quarter. But I will keep you posted once I learn more on that. Back to my slides. So, course website. I am doing things on my own website for reasons that are A, Brightspace is very annoying to update, and B, I have edit buttons. So if you click on the edit button that should be below every single page, you can create a pull request on GitHub, and then you can contribute things. So there are 100,000 tutorials, cheat sheets, YouTube videos on pretty much every single thing we're going to be talking about. It is an entry-level course after all, and I would like to invite everyone to contribute things that help you through this course. So extra information, supplemental things, an overview of something that I may have missed. Someone might explain some topic in some other way that might have helped you. And I think those things, if you find them and you think, oh, this might be useful for someone else, then it should be nice if you provide it to other students. Don't provide things that are just solutions. I mean, this course is about learning things, and copy pasting is not really learning. So an example of a good suggestion would be a cheat sheet of reading files in C, an overview of all of those functions and the errors that you might get, I don't know. A not great suggestion would be how to find Gattaca in genome.txt, because that is just the assignment. So that will be some grep line that you then can copy paste. Yeah, not super helpful. An overview of options of grep might be more useful, although I would point people to the manual. So lectures are during this time slot on YouTube. You can ask questions in the chat, and recordings will be made available, and they should have the chat with them. So then hopefully any questions that are asked make sense in context. And I would like to invite everyone to be there for the lecture, because otherwise I'm very lonely here. And the interaction hopefully really helps. I mean, this is the time to ask me a question if I explain something and I'm not being clear, because that means that probably I should spend more time on something, and if you don't point that out to me, then it will not happen, of course. And you cannot point that out to me if you're watching a recording. Tutorials are on Tuesdays during this time slot, and we are going to be, at least the idea is that you can collaborate and interact with your student assistants on the Discord. The reason for that is that we can make these voice chat channels where you can share your screen and people can join that very easily if you need help. People have also been using the helping each other channels already very well, and yeah, it is more or less the best we can come up with in a short notice, especially since the university doesn't really provide anything for us. Anyone who has ever used a Brightspace forum knows that those are not great. Outside of tutorials hours, though, the questions channel, where you can ask questions to the student assistants, will be closed. The reason for that is that I kind of still want you to keep to the normal schedule as much as possible, because I believe that that is the best way to get you through this course. And that means that that's on one hand, and on the other hand, otherwise the student assistants will get questions the entire week long, and they also like to sleep. And also the university will not pay for 40 hours a week of questions. So yeah, outside of those hours, you can use the Students for Students channel. People like me or the student assistant sometimes hop in there as well. But usually you should use that to ask each other short questions. And I think it's already been useful for a lot of people. If you don't want to use Discord, that's fine. Just send me an email so I can figure out how you can communicate with the student assistants. Okay? I understand that it is asking you something that is slightly outside of the normal data sharing things that you might agree to if you sign up for this university. And yeah, if you do have an issue with this, that is fine. Just send me an email. Handing in homework is mandatory. That means that you need to, we'll give you assignments, you've already seen the first one, and you have to hand them in by the deadline. Please hand in homework in pairs. The reason for this is very simple. There is 220 of you and only 6 TAs, and do the math. If you hand in homework in pairs, we can give feedback more efficiently. If there is too many pairs, then too many single people, then the amount of time we will need to grade everything just grows very big, and then the quality of feedback that you will get will just suffer. Sign up for your group in Brightspace. I believe that that is necessary before you see the hand-in thing, so do that. Hand it in on Brightspace, and if you have trouble with an assignment, always handing something. So if you said, I couldn't figure it out, and then just that is all the information that you hand in, then we cannot help you. I've in the syllabus written what you could write, and if you don't know what happened. But basically the thing is, think about what you tried, what was the idea behind it, why did that work, why didn't that work, what did you think, and then that gives these student assistants things to provide you with feedback, because then they can more or less trace your thought process and go from there. Of course, if there are special circumstances that cause you to miss a deadline, send me an email, and we can figure something out. Deadline is, this is a general rule, on 12:30 the week after the homework was assigned. So that is after the tutorial session, after when you got the assignment. There are things like May 5th and the break next week, though. So the deadline for homework you'll be getting tomorrow is May 12th, which is quite a long time away. But other than that, this is the general rule. Please don't forget that there is that deadline with all of the home partying that you might do during May 5th. Yeah. Finally, please provide us and me with feedback as we go along, because yeah, I'm starting my YouTube career also for the first time here. Like and subscribe. So please provide feedback either through the feedback channel or by sending me an email if you think that there's something that I am doing right now that could be done better, or in another way that might make more sense, or something like that. I also don't know how to best do things. I see a question of if the assignments are graded. That is a good question. They will get a good, sufficient, insufficient, fail style grading, like you are used to in other courses. The more detailed description of that is in the syllabus. In general, that is all just more to give you an indication of how you're doing, more than a summative grade. Okay, so that is this deck of slides. Then I need to switch to the other deck of slides. yes. So the C programming language. So this course is called Hacking in C. So you might have guessed that we are going to be using C in this course, and mainly we're going to be using the ugly features of it. No, the assignments will not give you a bonus. You will just have to hand them in. And trust me, you do want to do that. If you took the course before and are taking the course again, and that means that you already have solutions to some of the assignments, send me an email. You don't have to do the work again, but make sure that you actually still know what's going on in those assignments. Please don't hand in any work that you've already handed in before, because that's just a waste of time of the student assistants. So C, that is a programming language, and it was invented in the 70s, and many people say it's the first one because they just think it's very old and it is very basic, but it's not actually the first one. One of the examples that predates it by quite a bit is Algol. Another predecessor is B. C, B, you get where they're going with that. There's also actually a language called D, but that's something completely else. The development of the C programming language was very closely tied to how Unix was developed. So that is an operating system that then is a predecessor of either literal or spiritual of Linux. Mac OS is a Unix type operating system. Quite important in the history of these things. And Unix and Linux are mostly written in the C language. C compilers are available for many platforms, and by a platform I will I mean a chip. So like an Intel CPU or an ARM CPU, as you might find in your phone, or all sorts of embedded things, smart cards, and it's relatively easy to write a C compiler, so they're very ubiquitous. The language is very much still in development. The latest release is C18 for 2018. Popular other versions are C99 and C11. Then there is also compiler extensions. So the GCC GNU C compiler has a bunch of extensions on top of C18 that get you GNU 18. But the default version, the default version in GCC is GNU 11. You will not usually see that this is all a thing, because we will stick to the basics. But there are still things going on there. So C was initially co-developed with the Unix operating system. And as such, it's a language that's really aimed at programming for hardware. It's also sometimes called a systems programming language. And the idea there is that you can really tightly control what hardware is doing, because an operating system, of course, needs to manage hardware. That's the main thing it does, other than doing things for users and providing APIs to the hardware. So that's C was used to replace the assembly code that they first had written Unix in, and then later it's also used to implement new software for Unix. But it really gives you this close control that assembly also has. So assembly, there you have almost no abstraction. You're writing the actual, having no abstraction would mean writing numbers that represent all of the instructions. That is very annoying, so you need some abstraction, and that is the So in assembly, you do mov register A, register B, that get directly translated to the machine code that is run on the CPU. So that gives you really full control, and you need to do everything. You have no types, there's no bounds checking, because everything is just a bunch of bytes to the CPU. You have direct access to everything, or as far as the operating system will allow you to. And you can choose every single instruction yourself, and also even allocating registers is left to the programmer. So you do need to do a lot yourself. And the annoying thing is that different CPUs have different instructions, different numbers of registers, so you do everything from scratch if you need to move software from one computer to another. So they initially developed Unix for the PDP-7, some sort of old computer, and they moved that to the PDP-8 or something, a newer version at some point. And I think that it probably was very helpful for them that they had this language that they only needed to write a compiler for, and then you could take the code that you had for the old computer and just transfer it to the new computer. Yeah, another thing you need to do with assembly is that there's not only just the specific CPU that you have. So my laptop has an Intel CPU, but then there's also different versions of that Intel CPU. So that's a microarchitecture. Mine is a fairly new one, so it has things like AVX2 vector instructions and stuff like that, and older ones did not have that. So even if just a new version of the CPU comes out, if you want to get the most of it, you might need to re-optimize everything and for assembly re-implement all sorts of things manually. Every single year, maybe even. So C takes away some control because it will do things for you. It will do register allocation. It will do choosing some things. And what you gain from that is that C is portable. So in theory, you could take code from one computer and run it, compile it for another type of computer, and it will still work. In practice, there are some issues that you might run into. For example, that different compilers might often not be fully compatible. The Microsoft C compiler versus the GNU C compiler are very different beasts. And that you can, with effort, write code that will run on both, but it gets to be annoying sometimes. And you might need to muck about with macros to do things conditionally based on what compiler you're running your code on, and yeah, it just sucks. You also need to stay away from hardware-specific features. So if I start using Intel vector instructions, then I will not expect that to also run on the ARM core that is in my phone. Also, hardware-specific assumptions might be a thing if you write code that assumes a certain type of Endianness or alignment requirements or something like that. But if you are careful, you can write portable C code. You also need to stay away from implementation-defined behavior. We will talk about that later, but turning on this warning flag helps. So then you have C code that is portable, and then you have this compiler, which is a great tool because it can translate this more readable, portable, nice, for some definitions of nice code, to the target CPU that you have. So then you have this code, and it's very nice, and you can run it on your phone, you can run it on my laptop, you can run it on an Itanium CPU, you can run it on a PlayStation 3, in theory. And the compiler will also do lots of other things for you, like if you write a very nice advanced compiler, then it can do all sorts of tricks for you because it knows exactly what it's targeting to do all of these optimizations for you. And compilers have gotten really good at that, indeed. And what C does, however, still let you do is access memory in a raw way. So in that way, it's still very much like assembly code. If we want, we can still do everything very ugly ways. C also gives you types. We didn't have types in assembly because in assembly everything is just bytes. And it's very nice to have types because that means that if you write a function that expects a string and then you give it an integer, and then it says, I didn't expect an integer, and then it will give you this warning when you compile the software instead of after you've shipped it to customers. So you might be familiar with C++. So that was originally developed from C, but it's really its own thing. It is not a strict superset of what the C programming language is. So for example, this line of code is valid C code, but it is not valid C++ code because in C++ you will need to, C++ is stricter about types. So malloc returns a void star pointer, a void star type, and you would need to cast that to int star. But in C++ you should really be using the new keyword. It is easy to write code in C and then call it from C++ code though. You can use basically the same compiler, and this is commonly used when you write some high performance code where you have all of the raw control, and then you take a nice to use wrapper and you write that in C++, and then whenever it needs to use all of the speed stuff, then you just call out to the C code. This is not a feature that is restricted to C++. Many languages have a foreign function interface, is what it's called, to link to binaries that are compiled with C or from C. As an example, you have NumPy. That is a Python library for doing all sorts of mathematics stuff. Data scientists are very fond of it, and it implements many core maths operations in C for performance operations. So for example, big matrix multiplications, then you iterate all sorts of lifts, etc. And there's an efficient, very, very fast matrix library for that, and that is programmed as C. Then we get to the nice, getting more a bit into the details of how C works. So let's quickly step back a little bit before we get into it, and then we talk about the syntax and the semantics of programming language. So syntax is spelling. It defines what a valid program is, or what the language of a valid program is, and that's basically the semicolon at the end of a rule, the parentheses, the curly brackets that you need if you have an if statement that's more than one line, etc. The fact that function is a keyword, etc. Then there's also semantics on the other side of it. That is the meaning of a valid program. And in many languages, the semantics are fully specified. So if you have a program that compiles, it's also clear what it will do. It might still be buggy, but it will be buggy in some specified way. It might crash, or it will say null pointer exception, but it's at least clear what it will do every single time. In C, it is not fully specified. So in C, you will get that this will be a problem. There is first implementation-defined behavior. So some behavior, that is, you write some code in some way, and then it has behavior. And some behavior is unspecified by the standard. Specifically, the standard says, if you do this, then this is implementation-defined behavior. And the compiler must say what it will do then. And why they did this was that you can make a compiler more easily, because you can just say, oh yeah, but I will just translate this to this hardware instruction, and then I will use the behavior of that instruction. The other reason is that you can allow compilers to do certain optimizations in a more easy way because you can use the assumptions that you add. Often, so as I said, this is often specific to the hardware that you're running on. So even though a compiler might specify it, it will probably then also contain a list of things saying, if you run this on an ARM processor, then I will do this. If I run this on a PowerPC processor, then I will do this. If I run this on an Intel processor, then I will do this, and so on. So one of these things is that in which order this will be evaluated, because of course there is no such thing as doing things at the same time. The sizes of certain types, we will get to that. If the character type is signed or not, so if you can have negative chars or not. The number of bits in a byte is apparently unspecified by the standard, although there is supplemental things that say it needs to be 8. Yeah. For most of this course, basically, unless we specify else wise, we will say that we are running things on GCC 7 on a 64-bit AMD 64 CPU. So that's an Intel CPU is the same architecture. And we will also assume that we are running things on Linux. There was a question that if there is a large difference between compilers on the same architecture in this regard. Sometimes. So I have a bit later, I have an example where the Microsoft compiler differs from the GCC compiler. Namely, the size of a long on Microsoft is 4 bytes, and on Linux it's 8 bytes. Undefined behavior, though. Certain specific actions, so you do some operation or you do things in a certain way, are defined as undefined behavior. So it's not that the compiler doesn't say what will happen, or the specification doesn't say what will happen. The specification specifically says, if you do this, then something undefined will happen. So it's defined to be undefined. That means that when a program reaches such behavior, then one of the following may happen, or more of the following may happen. So it might crash every single time you run it. As far as undefined behavior goes, that is fairly okay, because then you at least know something is wrong. It might also crash 0.01% of the time. That gets very annoying, let me tell you. It could also just crash not when you test it, but only when you use the code as part of some other code. Also very fun, if I can tell you. It could also just delete everything on your hard drive. Not likely that the compiler will emit code that does that, but it would be allowed behavior. It could also murder some puppies. It could light your house on fire and do all of the above and still give the right result. You don't want to get into situations with undefined behavior. The existence of undefined behavior anywhere in your program makes the entire thing meaningless. And that is because the compiler uses undefined behavior to do that, and the assumption that it is not there to change your program in certain ways to optimize it, that might break everything. So the compilers assume it doesn't exist, and that they mutate your program in ways that might change the meaning. Often the presence of undefined behavior will lead to exploitable security problems. So the most famous one is a buffer overflow, which we will be doing a lot in this course. And that is a classic example of undefined behavior. Usually you get segmentation fault. We will be using it to do more productive things. So accessing memory out of bounds is the classic example. reading of uninitialized memory. So you have an integer x not equal something, but just integer x, and then you read it. Division by 0. Dereferencing a null pointer is a great one. Integer overflow on signed integers. So for unsigned integers, this is defined behavior. Then it will roll over back to 0. But for unsigned integers, it's not valid. No, for signed integers, this is not valid. Left shifting a signed integer, because then the first bit more or less indicates if it's negative or not. So what happens when you shift that? Shifting something by more than the size of the type. So a character is 8 bits, we shift it to 100 bits. What does that mean? Many examples, and you would say that many of these, specifically if it's hard-coded like this this shift, for example, the compiler should be able to really easily say, yeah, that doesn't make sense. But for weird reasons, often these warnings are turned off. So make sure you enable -w all and -w extra when you compile code, because only then will you get many of the warnings that will help you write correct software. For writing incorrect software, it doesn't matter, of course. Another example is returning nothing from a void function. So this function f is written such that it should return an integer. It doesn't. C compilers might happily compile that for you, and then you get undefined behavior. Okay, so this other thing that the compiler does is it gives you things that are more than just bytes in memory. So let's start with values. Typically what you do in a program is you do operations on certain values. So you might add two things together, subtract them, do a multiplication. And in your assembly programs, if you write stuff in assembly, you will need to very carefully manage where you store things. You have a limited number of registers. You often need, you run out of them, so then you need to put values and park them on the stack and then get them back later, and you need to manage the stack. Super annoying. And the compiler will do all of that for you in higher level languages. So when you call a function such as this function, you will pass it the value of, in this case we call f with the value y, and then you pass it the value of y. This is called call by value. And what that does, it makes a copy of y. This should not be x, but the argument, it will make a copy of that, so that if you write the following line, so we assign 10 to y, pass it to f, and then you will see that y did not change because it was passed, the function f was passed the value and not the not y itself. But we also, in C programs, have addresses. And addresses are special kinds of values, and namely it is the address of where this variable is in memory. So if you define integer a, we can get its address through &a. This is called a pointer. And I think that this is a good time to make a break, and then we will talk about pointers some more after, let's say 15 minutes. So let's resume at 16:45. And I think that in the meantime, that should give everyone enough time to refill their coffee if they want to. And then I will resume then. In the meantime, you might be asking me questions. So if anyone has any questions, this would be a good time to ask them. Otherwise, I will see you. I see a bunch of questions. I run. Okay, many questions. What Linux distro do you run? I run Arch Linux, but that is not very important. Person with, is that Chinese or Korean name, needs tech support. I cannot answer that in detail at this moment without more details. Maybe go to Students for Students. The exam will be assignments, probably. I don't know yet. Probably. Assignments, so a bunch of things like how we do the assignments in the week. Normal weeks, you will need to hack into something or something like that and write a short 2-page or something report on that. I will get back to pointers later. Is there a way to share a folder with another science account on Lilo? That is a good question. Not easily. You need root to do that. I will also take a brief break and I will get back to you at 45. Okay, so I think we should be getting back to it. So we were talking about pointers, and we have this ampersand operator, and that will get you the address of a variable. And then you can obtain a pointer to A. And we denote that as the type of a pointer is the type of the pointer to data with the star at the end. So that's why you might see int star as a pointer to an integer or char star as a pointer to a character. And you might see many of, good point. Slides. So you see here type star, that denotes the type of the thing being pointed to, and then the star at the end. We will return to these things later. For now, you just need to be aware that such a pointer is also just a value. You can convert it. It's also even just a number, because the address is just some number that is where the memory is. And you can also convert things from pointers to numbers, or even you could convert a number to a pointer, but often that won't make sense, of course. If you pass a pointer to a function, then you pass the pointer by value. But because you then have the value, the address, then you can access the original version of the pointer to data. That is all stuff that we will get to in the next lecture, and a bit at the end. Yeah, pointers are quite a big thing, and we will talk about that more. But for now, just know that using this ampersand will get you an address. Then there's a bunch of other types. So hardware only understands memory as a bunch of bytes. It knows that it can do certain things on bytes, but it doesn't know what the bytes mean, what the bytes themselves are. It just takes bytes, does thing. Even if that wouldn't make sense, it will just do things, and yeah. Bytes are 8 bits, and when you write software, usually it helps when you define certain semantics, and types are a tool to let you do that. It's helpful that the compiler will give you an error when you call stringlen, which will give you the number of characters in a string up to its terminating null character. And if you call it with stringlen and then a 3, that is not a pointer to a string, to a character array. So it will tell you, yeah, this does not make sense. And then you know that there's a mistake there instead of just doing segmentation fault, cannot access things at address 3. You can program many things without understanding how these types map into the underlying hardware stuff. But having that extra knowledge will help us have more fun. And that's basically what this course is about, having fun with the C language and everything it breaks. So let's start with the most elementary data type. That is a char for a character. And almost everywhere they are exactly 1 byte. There's this standard POSIX that says that how operating systems, portable operating systems, something or other, you can look it up on Wikipedia, Windows, Linux, macOS, they all implement this standard to some extent, and POSIX says that 1 byte is a character, or a character is 1 byte. You can use chars to store characters. This is something you might have seen also in C++. But it's really an integer type. It can store any 8-bit integer value, and even the quote characters and then something between them are directly mapped via the ASCII tables to numbers. So when we have these 3 lines here, the char A equals the character 2 ASCII 2, the character B, char B is 2, and char C are 50. These are the number 2 and the number 50, and in fact, A equals C because ASCII 2 is 50. Writing stuff like this, where you have a character A and then adding some number to it, is also completely valid because, again, something between these single quotes is just a number, and you will then can add numbers to numbers, and it will result in D or 45, 44. The second, there are some, first this. So how many times will the following be printed is a nice thing. So we have, or not so nice, we have this character I, it's an index, and we set it to 42. As long as it's greater than 0, we will print this string, and we will go from 42 to 0, and then how many times will this be printed? Well, I already previously said that characters are signed or unsigned depending on the computer you run it on. So this is a trick question. If it's a signed value, then character is between minus 128 and positive 127. If it's an unsigned value, it goes between 0 and 255, and when you reach 0, it will go back to 255. And because this thing says greater than or equal, it will loop. On AMD64, so that is my laptop, your laptop, character is a signed value. So this will terminate. It will go to -1, stop, everything is fine. On 64-bit ARM, character is an unsigned value, so this will loop forever. So usually you should always write either signed char or unsigned char whenever you want to write code that should also maybe run somewhere else at some point. Then there are a bunch of other types that are very important. There's the short type. This is in order of size, and that is at least 2 bytes large. Almost everywhere, I think it's 2 bytes. Then we have integers, ints, and they are typically 4 bytes, but there are some chips on which they are just 2 bytes. If you assume that something will fit some large number that doesn't fit in a short, and you put it in an int, you might run into trouble. Then there's a long. It needs to be at least 4 bytes. It's also often 8 bytes. And on Windows, it's 4 bytes on 64-bit Windows. And on 64-bit Linux, it's 8 bytes. So again, if you make the wrong assumption here and then you compile code on Windows, then you might fuck up. Then there's a long. That is always at least 8 bytes. And pretty much exactly 8 bytes every single time. Then each of these are in a signed and an unsigned variant. So if you just write short, then you will get the signed version. If you write unsigned short, you get the version that's between 0 and whatever fits in that number of bytes. You might also sometimes see short int, and that is because you can write long int, long int, or short int, and you could just leave out the int and it will still work. You could even just write unsigned and you get an unsigned int, but that's just ugly. There is this operator called sizeof, and what that does is it will give you the size of a type in bytes. So I could write this line, and this is a printf with a format string, and I will get to that later. And it will print the size of the integer type. You can also do that with a variable. In this case, we print the size of the variable x. The compiler will figure out at compile time that this is, if I would run this on my own computer, it will just give you 4. Finally, we can write integer literals in decimal. So that's the Arabic notation that you're all used to. There's also octal notation, which is sometimes useful, not always useful. You can add a prefix 0 to something. So 0377 is not 377. Finally, there's a hexadecimal notation where you prefix it with OX. You're probably more familiar with that one. And all 3 of these values are 255. So there are some other integer types that are nice to know about. So there's a special type that indicates sizes, which is size underscore t, so size type. And that is used by, for example, sizeof, or expected as the argument for malloc, for memory allocation, because that is the type that is sized so that it will fit any pointer. So if you would allocate the entire memory and then take the size of that, then you should still get something that fits in that integer type. So that's where you have this size t type 4. Pointers also have a specific size. On AMD64, pointers are 8 bytes long, though only 6 are used. There are also some nicer types. So all of these varying sizes of int, etc., make it super hard to write efficient portable code, because I don't know if I'm going to need, say, some value needs 4 bytes of memory. So then I need to use int, but int could just be 2 bytes maybe. So I will need to go to long, but long might be 8 bytes on Linux. So then I'm using too much memory. It's just a big mess. So the C99 standard as this header standard int which gives you these types that have exactly a fixed size. So uint8t is an 8-bit unsigned integer. In fact, it's just an alias for unsigned char everywhere, but you see that it will go down the line to int64, and you have all of these types at the logical increments of sizes. And these are useful because you can just look at them and just know how large it's going to be and not run into annoying trouble. There are also 3 real types, so that's for the behind the comma numbers, float double and long double. There's also complex types. We won't be using that much or at all. This article explains you all of the ways in which this is super annoying. These comma numbers, I mean, they're useful for a lot of things, but also super annoying because, I mean, you can have some number and then add this weird constant and then subtract that same weird constant. And what will that do? It will round it to a set rounding mode. Very, very annoying. Let's take a step back to printf because we've already seen it a bunch of times. So printf is a function that can print a string according to some formatting. So print formatting, printf. So this is instead of cout, what you might have been used to in C++ with all of the arrow notation and then weird formatting specifiers in between, etc. Printf works with this percent notation. So we have %d for digit, %u for unsigned integers, %x so you can print in hex, octal. Then there's these modifiers. So this is %u, but then with the L modifier, that means that you're printing a long value. Same for long. You can print pointers, so this will print the address of D and format it as a pointer. Float, long float, double float. Then there's we want to print an unsigned value, but it needs to be the size t width. So then there's this ZU function that we saw already. And then finally for the uint dot types, there are these special macros. They come from inttypes.h, and you can need to use them in a slightly funky way. There's examples in the manual of inttypes. And you can use %. And what happens is, see, if you write 2 strings next to each other, like double quotes something, quotes close, and then quotes open something, quotes close, it will be seen as just one string. So this macro will expand to whatever the formatter is for uint8t. And we have those also for uint64, for example. So the thing is free for print or something, then the U in this case for unsigned, or the D for signed, or the X for hex, and then the size of the type. Yeah, this is a slide that you might come back to at some point. Another good way to figure out all of these format characters is to go to man printf, man3 printf specifically, but Googling for printf formatters also usually helps. We have types, and that we sometimes need to convert between those things. So if we have all of these float values, then we have pi equals something, and then the radius of a circle is 2 times pi times the radius. 2 is not a float. So if you want to, you would want to get the answer here that makes sense. So usually you can convert types. And what's usually done and what makes sense to most people is that you go from less specific to more specific. So that's done here. We go, this is seen as a float to, and then you just compute the circle with the numbers behind your comma. The other thing that's usually done and that makes sense is that when you go from a wider type to a smaller type, then you will just throw away the top bits. Some of these cannot make much sense. So this is an unsigned integer, 1, that we're here. And this is the signed integer b minus 1. If b is less than a, what will happen here? That is a good question. Will this be converted to an signed integer? Will this be converted to an unsigned integer and then be super big? I'm not actually sure even. If you enable compiler warnings, this is the type of stuff that you will get warnings about. If you don't enable compiler warnings, this might go by you unnoticed. And you might get all sorts of behavior that is very stupid. Sometimes you need to do explicit conversion. For example, this multiplication, if you multiply two 32-bit integers, you will get a result that's also 32 bits. By default, this multiplication will give you a 32-bit result, and that because, however, if you multiply two 32-bit values, you get a larger result than 32 bits. Int marks times int marks is larger than int marks. You can fix that by casting either one or both of these factors. So this will convert A to a uint64t, and then multiplied by b, and b will implicitly also be converted up, and then you will get the big result that you're looking for. You can also use this to, for example, truncate float. So if you convert a float to an int, and then back to a float, then you get a 2.0000, maybe 1. Does not work always, though. There are sometimes issues. So this is a nice example of what will happen. The question is, of course, lead it into a bit, and the answer is undefined behavior. So if we convert this unsigned character to a signed character, signed characters can only be up to plus 127, and this is one larger. Signed character overflow is undefined behavior. So this might print minus 128 or light your house on fire. One of the two, no way to know. How are we for time? Oh, we still are quite good on time. So integer representations. These, I will get into that right now again. Signed is negative numbers, numbers that can be negative numbers. So a signed integer is a number, and then the sign is the plus or the minus character, more or less. We can do a signed integer, and you could store that as the absolute value, so 3, and then if we also separately store the, is this a negative number or is this a positive number, part of it. Then you get a redundant representation for 0, which gets to be annoying, because then you need to special case that, check that, etc. And it takes extra storage. So they invented, there's this other idea that you can flip all of the bits to obtain minus a, and then you have half of the storage, more or less. That's known as one's complement, but then you still have 0, namely all of the bits are 0, or -0, where all of the bits are 1. Still annoying. So what is typically implemented, I think everywhere, is that you use 2's complement, and that is flipping all of the bits first and then adding just 1. You can check that this works by computing minus minus 1, minus minus a. So say a is some value, then we flip all of the bits and add 1. And then we can flip all of the bits and add 1 again, and then it should get back to the original value. And if you do that, you can check that that will work. And that will give you the following range. So a k-bit signed integer goes from minus k to the minus 1, 2 to the k minus 1, to 2 to the k minus 1, minus 1. So for this 8-bit example, minus 128 plus 127. And there's also some hardware niceties for this. If you implement this all correctly, you can use the same hardware, so the same wires and chips, etc., to do both unsigned and signed addition, because it will more or less work the same way. Then there is the fact of how do you get numbers into memory. Say we have this number, which is in hexadecimal 11223344. Typically, when we talk about putting stuff in memory, we'll see that we'll do it in hex, because 2 hexadecimal positions are, or one of them is 4 bits, so this 2 is exactly 1 byte. And we can put them into memory like, so these are the low addresses, and then we go up. Like just from the start, 11223344, or we could do that around. We first write 44, then 33, and then 22, and then 11. The question is, what is more intuitive? And yeah, it's a bit hard to get feedback here, so I'm just going to continue. There's another way we can represent these integers. We can write them as a polynomial. The sum over some bytes times 2 to the 8 times I. So that is times 255 times 16 something. And the AI are the bytes of the integer A. So if we write this, then we have either A0, A1, A2, A3. See that this matches up nicely with the memory addresses, or the other way around. And then again, does this make more sense? So putting the least significant bytes, that is the bytes that have the least meaning, they are the ones and the tens, not the hundreds and the thousands. Do you put them at the end, or do you put so that's little endian, or you put the most significant bytes at the low addresses? So then you put A3 will be the most significant bytes. Do you put those there, or do you put those there? Then these two types of endianness. You probably have seen this before in the processors course. And yeah, little endian or big endian means where do you write, how do you write these things down in memory? And most CPUs today, almost all of them, use little endian. There are some big examples of big endian CPUs, CPU architectures, and that's, for example, classic PowerPC or UltraSpark. They are pretty much dead, I think. The classic PowerPC was used in MacBooks before they switched to Intel, for example. There's also architectures that are both big endian and little endian. They can switch between them. But So, for example, ARM or the successor to PowerPC, Power 8, and later, they can be run in little endian mode or in big endian mode, but you will see that typically they are used only in little endian mode. So Power 8 is, you can download Ubuntu for that architecture, but Ubuntu only offers the little endian version of it, and the big endian version you need to, if you want to run Linux, I think buy Red Hat, some enterprise version of Linux. And you might think, why the hell do we do this way? It looks all wrong. And that the problem is that we write left to right, but then use numbers that go from right to left, and then you get confused there. You might ask, why do we need to know this? We will get back to this after a while once we start to write addresses in memory, but you also see that when you're dumping reading stuff out of the memory, that we will see that the numbers might be in a different order than you might expect them initially to be. So back to addresses. So on 32-bit processors, x86, so that's the 32-bit Intel or AMD processor, addresses used to be 4 bytes. Exactly the same as integer, aligns very nicely. But yeah, you ran out of memory after 4 gigs, I think. So current AMD 64 processors support up to 256 terabytes of RAM on a single CPU. That is a lot. And that means that you need 6 bytes to represent 2 to the 48 addresses. But they still use 8 bytes. And there is these 2 address ranges where they start with, if you look at the first bytes, the upper bytes, then they start with 0000 up to 007FFFFFFF. Or you have the bytes in FFFFFF80 up to FFFFFFFFFF. On Linux, the first ones are user space. That's what you'll see when you are running your programs. The second address space is used by the Linux kernel. So when you try to access that and you are not the Linux kernel, you will get an error. There's also this bit in between, and that is defined to be not used. I'm not sure why they did that, but they did that for some reason. Back to pointers. So we can print the addresses of variables. So I have some random number here, the value 4, and we can write this pointer. So the type of this thing is a pointer, the star, to an integer. The OX just means that we're using hexadecimal notation. The star here means that we are defining here a pointer, and it's a pointer to an integer. So that's why you see int star. And we take the address of A. Then we can print the value of A. We can print the address of the variable. You see here that we use A or ampersand A. We can also see the value of the variable A pointer. If you take just A pointer, and it's a pointer type, so we will use %p again, and you will see the value pointed to by A pointer. And this is called dereferencing. So if you take a pointer and put an A in front of star in front of it, then we will dereference it. Then you will tell the compiler to, okay, this thing is an address. Take this address, go to the memory, and then in the memory load what was there. And then we will see that it is 4. So you will see indeed that here we have this pointer, that the value of it is the address of A. Makes sense, ampersand A, ampersand A. And the value pointed to by the pointer is 4. And you also see that these addresses are quite large. So they start with 7, F, and then some garbage. They are stored very high in user space memory, and that's because int is a stack variable. If you just write int a equals 4 in some function, then it will be put on the stack, not on the heap, which we'll get to later. And a stack variable automatically managed, very nice, etc. But the stack starts from the very high addresses, and so more or less from the bottom, and then grows towards the lower addresses. There's also the heap. There we can get that we need to manage manually. So we request memory somewhere, and then we take the size of an integer as the number of bytes that we need. We will get a pointer back, so that's why you don't see the int a here. And we can write to the location where that pointer is pointing to by writing this. So we take star a pointer. So again, a pointer is the address. We tell the compiler, take the address, go to the value, go to where it is in memory, and put the 4 there. And then we'll see that, again, we have this address, and the value is again 4, and we again need to dereference the pointer to get to the value, go to memory, go to the memory where this thing is, and see what is there. And the value of a pointer is just again an address, and this is some address halfway in the memory space, and that is because this is a heap address, halfway user space memory. And the heap again is manually managed. If we don't call free at the end, we will be leaking memory, but get to that later down the line in this course. And yeah, again, we have been writing this star thing to get, okay, this is an address, go to where it is pointing to, and then look there. Yeah, I am still quite good on time. I hadn't expected to get to these slides. But there we are. For homework this week, there will be some assignments at the end that will use pointer arithmetic, and that is using pointers and then doing operations on the pointer and then dereferencing the pointer to do things in memory. It is not super complicated. I've linked a YouTube video that also tries to explain this to you, but it might be, it will be something that I will explain next week. The reason for that is that getting into all of those slides is a bit more than we can chew off this week. You will have until May 12 to do this assignment, and that should be ample of time. I will upload the assignment soon, TM, but yeah, what else did I have to say? Yeah, so you will have the tutorial session tomorrow, and then again a tutorial session on May 12th. And then there is the deadline for this assignment that will be published soon. Okay, so there are a bunch of questions. Yes, I will upload the assignment soon. I will upload the slides and put them on my website with a link to the YouTube video, so you can find things together. The time of the lecture. I was not aware that the university shifted all lectures to start at 30. I'm used to 45 because I'm old. Last year I was thinking I probably was doing things in the morning. Today I learned we can start at 30 if people would prefer that. Probably makes sense to have dinner a little bit earlier. I changed this year. Say, so you know what the thing is? They don't communicate. This is something that they haven't told to staff in an email or something like that. Like, yeah, it's super annoying. Yeah. So yeah, it's a thing. The university was also very great at communicating either lots of other things. And yeah, with regards to lecture times, I figured that there might be one or two of you who took their phone that they're listening to the lecture to and went to the bathroom. So it's probably not too big a deal. Are the yeah, I might say some more things about the exam in more detail. The thing is that we used to have a paper exam, and it's probably also still scheduled as such in the roster. The thing is that the type of exam that we used to have is not very conducive to having Google available. It makes a lot of questions a bit pointless, and it is yeah, so then there's the option of either trusting all of you guys, and while you're all very nice, etc., the temptation is maybe a bit too big to let that happen, or use this Proctorio bullshit software. The university is looking into things that use the webcam to monitor everything, etc. And it does not seem to make sense to do that in a course where we teach you to break things. So also it's just horrible. So it seems like this course would be better suited to a more practical examination. How that will look like and how many exercises there will be and how much time you will have for that are still up to deciding. I need to figure out what to do there and do things. It will probably be in the week before the formal exam time, and then a deadline at the exam time, and that you will do some hacking into things, and I will try to make that an individual assignment in the sense that I can tweak some things and generate things such that everyone should have their own thing. And then also have you write a report about, okay, I did this as first steps to learn this information, and then use that in that way so that we can figure out a little bit of what you tried, what you got, what you didn't get, so we can give people a grade also if they don't get to the end of all of the or some of the assignments. I will get back to the discussion in chat now. Do you need to have the star in front of every value assignment to a pointer? Like in the second line, a pointer equals 4. That is a good question. If I leave this star out, I am assigning the value 4 as a pointer to a pointer. So that means that I have a pointer, and it would print OX4 here for the address. And then you would dereference that, and you would try to get what is stored at the address 4, and then your operating system will say, that is not your program, and it will terminate what is going on. So you will get segfault. What segfault means is that you are accessing something that is outside of your program. So that is why we have this star here. It's very important to indicate when you do this assignment that we are storing it at the address instead of storing an address at the variable. Yeah. That is a thing. I will have pictures next week about how pointers work with arrows and things. So if this still is a bit what's going on here for you, rest assured we will get to that next week. But maybe in the assignment there are already some things with pointers. Try to see what you can do, stay away from what you can't do. You should be able to do like half of an assignment sometimes and then fill in the other half later. Yeah, and I think that means that it is now almost time to go to the non-work room for most people. Yeah, if you have any follow-up questions or something, I would like to point you to Discord. So where did I put Discord? Screen capture. There is the nice lecture chat channel where some of you have been already chatting amongst each other a little bit. This is the Students for Students channel where people have been helping each other to try to figure out some things amongst each other. Questions is the channel that you've probably seen already during the tutorial last week. For those who missed it, we tried to clear it up so that it's not a confusing room with all sorts of answered questions. Student assistants will typically contact you privately if you ask something here, and then we'll delete the question after it's answered. FHQ contains frequently asked questions. It's often wise to keep an eye on it. If something affects many students, we might post something here. And then there's these off-topic channels. So if you have problems with Discord, I've copy-pasted or stolen description from the Discord of object-oriented programming. And there's the Mercator1 channel where you can post memes if you want. It's more of a channel for people to relax a bit in, although I might also imagine that you might want to do that in a Discord chat where your lecturer is not watching you. It might still be useful to some things. For the assignments, you need to do things in pairs again. So there's this partnering channel where you can find other people to work with who are still looking for a partner. So there's, for example, Chris here, and he's looking for a partner, and one of you might get the idea to send him a DM. Same for Papa Bear. Might be wise for the people who have posted here to edit their messages once they found someone, and people who are looking for a partner to first message these people before they post their own request, because otherwise it's a bit pointless. Lols indeed. Yeah, we will get back into malloc more when we talk more about the heap. For now, you can mostly ignore it because we will be staying on the stack. And an integer stores 4 bytes of memory, so you can store indeed values larger than 255. You can go up to whatever fits in an int. Look up integer types in C, and then you can find all of the exact values that you can store in there. There's the admin channel as well, but I'm not showing it to you. With that, I think this is time to round off this stream. So I want to wish everyone a nice week. Good luck tomorrow at the tutorial, although I'll also be around on Discord. And yeah, then have a nice May break. And I will see you on not next Monday, but the Monday after, where we will be talking about memory more, and we will talk about pointers, alignment of values in memory because there's some speed things that the compiler is doing there, and whatever else I put in the syllabus. So see you then. Bye. Thanks for watching. And yeah, I need to make this YouTube career work for me somehow. So please like and subscribe. If I get 1,000 subscribers, I can enable that YouTube money for me. See ya.